Cool. So today we're going to talk about two things. It's mainly going to be about CNN architectures and partially going to be about CNN applications. So we've seen what a convolutional neural network is. We've seen that there are certain parts or components of convolutional neural networks. There are there are kernels, there are or filters. There are convolutional layers. Essentially, there are pooling layers, and there are combinations of different layers that result in certain architectures. But what is the right set of combinations that really works out? And that's a question that many people have tried to answer by exploring different kinds of architecture. So what I want you to take away today is the intuition behind these kind of architectures. I am not talking about these architectures so that you know that this is a cool architecture and you have to use this. No, that is not the case. There are newer architectures coming out literally every couple of days, and you might find some architectures to work out very well for some applications and perform really poorly on other applications. So again, it's very specific. So there is generally, it's super hard to say which are the right architectures to use, but there are certain popular ones that people have applied in multiple applications and they've found to be good. So what we're trying to do is distill down, like, when they built this architecture, what were they thinking? And that is super useful because that allows you to start thinking of, so if they designed this architecture with this experiment in mind, then how do I create more experiments to design my own architectures? But before getting into architectures, it's been a couple of weeks and we've been, especially if you notice Mola, he talks a lot about like these things, floating point operations, processing speed, computational requirements. And this becomes increasingly important when it comes to architectures, because a lot of architectures, and he just mentions this in his videos, but he says these were trained better, or there was a lot of work that went in behind writing this architecture out. And these things are important to understand, because you are all machine learning researchers, but you are all also going to be required to do machine learning engineering work when you design research methods. So either you do it or you have a team that does it, but someone has to put in a lot of engineering work to do machine learning research. And so one of the things that I find it interesting to track, and this may or may not be really related to the lecture, but when I start looking at the industry, when I first started out, like thinking of, okay, the computation stuff, the memory, the footprint, and all of that, there was this interesting idea that came up. And some of you might know this already. So I'm going to talk about it for the first 2-3 minutes, and then we'll switch back into the actual topic of the lecture. Um, Gordon Moore, who was the Intel co-founder, said this, I think in 1970s or 80s, that the number of transistors on a microchip doubles every 2 years. Now, why do we care about this? Well, basically, a microchip is the basis of computers. So, what he's saying is that there is a certain pattern that is followed in the industry in terms of how progress happens. And so it was actually interestingly observed that yes, Moore's law does hold. And over the years, the different kinds of transistors that have uh, uh, been developed seem to have the number of chips, the kinds of chips that have been developed seem to have the number of transistors and integrated into it, doubling roughly every 2 years. But at some point, Intel actually failed to stay on top of this law. So Intel's co-founder created this law, but Intel actually stopped following this because they found it hard to create transistors that are doing better, create chips that are doing better and better in terms of having more and more transistors. But and so some of the people started asking, like, hey, well, is Moore's law dying? Like, is there a finite limit to adding more transistors on chips? And I'm going to pause there and ask you, well, anyone who has some idea, like, how do we fit more transistors onto the same chip?
Small size thing like that, making them fit to
that's fairly straightforward. The smaller you make your transistor, the more of them you're going to fit on the same chip, right? And interestingly, I started looking this up, and it turns out that uh, someone else might be a much bigger contributor to making chips smaller than actually companies like Intel, because Intel uses a machine, or I think Intel uses a machine by a company called ASML, who actually build these machines to design these chips. So in other words, they sell machines that make chips to chips manufacturers, and then Intel scales it and other chip manufacturers scale it. But it's interesting that then progress is sort of limited by what is the smallest transistor that this ASML machine can put on a chip. And so it's like, this is just from tracking an industry perspective. This is what turned out to be interesting. And so one of the things you realize is more transistors is equal to more heat. So the smaller you build chips, it doesn't necessarily mean more performance. You still have to work on cooling and all of these things that have to do with data transfer between the chip. And so I'm quickly going to give you like the punchline of this. The simple solution to this then was to build slightly bigger chips, but then chip size is limited by, you can't carry a laptop that is bigger than yourself. You really don't want to go back and build laptop computers that, like the old ages, were occupying entire rooms in buildings. So there is a certain trade-off that happens, and companies have emerged, especially these days, in the last decade or so, in 5 to 7 years, that started building much bigger chips. And this slide particularly is from a company called Cerebras, which got a lot of press in recent times because they built a chip that seemingly has 1 trillion transistors on it. I don't even understand what exactly that means. In terms of, does performance scale linearly with those transistors? Do you need some more, like, just adding more transistors will also create more heat, so your cooling has to be that efficient. And typically what happens in these cores, like when you utilize these transistors, you don't actually utilize them to their 100% potential, and you don't actually utilize all the transistors at once. So you realize that there is a lot of software stuff that goes into this as well. So this is just a comparison between the size of Cerebras's chip and the size of the largest GPU at the time. um, so 2.6 trillion transistors versus 54 billion transistors. That's the size difference that occurs. And still, like, Cerebras seem to be the industry standard in terms of power, in terms of throughput. So again, they're just giving you a sense of like what sorts of developments you might want to track when you're thinking about computational efficiency, and when you build deeper networks, what sorts of hardware are you going to run these networks on? Because a lot of times what network innovations will tie in with is hardware innovations. Currently, the reason Google built TPUs is because they realized that AI is a good bet to make, and they can design networks that work efficiently on their own TPUs. The reason Apple, and that goes back to the reason Apple is such a good company, or has such a fluid experience, is because their software is deeply integrated with their hardware. They control everything end to end, and so they don't have to make any compromises. Everything is seamless. So this the same idea, like when you're thinking about neural network design and like optimizations and like how the heck people do what they do, that makes things run so smoothly and fast, that is part of what you might want to look at. And I'll quickly get through this. One of the interesting things that actually came out, like when I was thinking of how the heck Cerebras did this, I just read their white paper, and this one point should be noted. When you want to run these libraries like TensorFlow and PyTorch on Cerebras, it actually extracts the computational graphs and translates it to some internal representation. They built this language called Claire, which is a certain, I think, graph compilation language. And so once they have this compiled graph, then they can use their GPUs and execute the graph. And this allows them to, if TensorFlow changes or TensorFlow has some breaking changes, that does not necessarily mean that it will fail to work on Cerebras, as long as they still have this the ability to extract the computational representation. They can still execute it in an optimal fashion on their GPUs. So cool stuff. Unrelated to what we're studying, but let's get back to deep neural network architectures, and we can think about hardware later. So the LeanIt architecture is what we're going to start with. This was around the 90s. The reason they developed this architecture was, I believe, to solve some optical character recognition problem, where and so when someone shows you this complicated diagram of architectures, and now this is purely opinionated, like what I try to look for is just the kind of number of layers, the dense layers, and the size of convolutions, because that will typically tell you what sorts of data they expect. Are they reducing the representation of the data dramatically? How deep are they going, and like what is the output like is it super this just has, for instance, 120 layers, 120 output neurons, not output neurons, I should say 120 hidden neurons that go to 84 hidden neurons that go to 10 output neurons. And so it's not that much of a compression. And it's fair because this was the 90s. They didn't really have deep neural networks. They just call these deep nets. I don't remember actually. But anyway, the idea was optical character recognition. So you have a 32 cross 32 image. I believe we've spoken about how an image is just a matrix of numbers. So this was just black and white. You have to identify the numbers on this sort of white background. And the numbers might be shifted and all of that. So you have to deal with those problems. But exactly the problem that they were solving is handwritten digit recognition. So stuff that is written on checks and postcards, and someone created this data set that they called MNIST. And the idea behind MNIST was, okay, if we have to do character recognition, why not just create a data set of characters and then create a set of 60,000 training items, 10,000 test items. These are very simple 28 cross 22, 28 images. They're black and white, so there is only one channel. Remember that channels had to do with colors. So RGB images have three channels, R, G, and B. And each of the channels have some sort of data that combined makes your color image. Anyway, MNIST was fairly simple. It had only one channel, and it had 10 classes. So the problem at hand that they were solving was something like this, where you can see this, the pictures passing through in the center. You can see the feature maps being feature maps being created based on these images. And so in the initial layers, which is on the left, you see that the feature maps are basically doing some sort of edge detection. And at the higher layers, they are developing some sort of feature representation that is not really the simple one, or like it doesn't really look like numbers. So it is some combination of lower level features that are being condensed into high level representations, and that is actually being used to predict what sort of number is passing through the slides here, right? So that's essentially the idea here. And the question that so in general, like for such networks, it's expensive to have the real cost comes from these densely connected layers, and that is because there are just a lot more parameters to optimize compared to the convolutional layers. And that's about all I wanted to say about LeanIt. Fairly straightforward implementation. Ignore the language here because most of these languages have similar sorts of functions to call. But if you're writing neural networks, I believe this is in Gluon. Yeah, this is Gluon. So anyway, when you're writing neural networks, you just want to add these layers in a sequence. That's the idea here. Cool. I don't want to say anything about that. And so the questions you really want to ask yourself in order to actually take something away from this lecture is, okay, if we have some architectures from history and we're getting to architectures in present day, what sorts of innovations do we create in order to create architectures in the future? So if you had to build a new architecture tomorrow, what sorts of experiments would you create around convolutional neural networks, or like just image recognition and image segmentation, and any sort of challenge that you pick? that tell you more about what direction you should build new architectures. Second thing we'll get to, and this is more towards the end of the lecture, what are some important problems to be solved. Um, the third thing I sort of hinted at by getting into the whole idea of hardware is how did progress in one field affect others. So at the time that Jan LeCun built and others built LeNet, the idea was that they didn't actually have a lot of compute available. And we'll see a couple of slides about that. So how did the availability of compute impact the depth of networks, or really that allow the depth of networks and training? And the final question you just want to get a sense of is how can I stay updated on AI research? Because every year there are thousands of papers being published. So what can you do to distill this down? And this is not a question that is answered in the slides, but more of I'm giving you the intuition for like things that matter and how to take away from a paper. This is what they did. This is what's useful to me. Cool. So with that, let's get into AlexNet. So with AlexNet, the architecture, if you look at this, it seems sort of similar to LeNet, where there are some convolutional layers, there are some max pooling layers. The layers are uh, uh, um, followed by the same dense layers that we had before, except now these are just much, much bigger layers. So now you can see that this is going to a 2048 fully connected layer, and another 2048 before dumping down to 1,000 fully connected layers. And the takeaway here is the number of parameters is really blowing up. So you have a lot more parameters to optimize and learn the right weights for this, which means you might not be able to learn as much with the same amount of training or the very small amount of training data. So you need more compute, more data, better learning strategies, training, call it better training, call it better optimization algorithms, what have you. So again, like not particularly caring about the architecture, but giving you the intuition that earlier, like in the 2000s, there were these ideas of kernels where right after this LeNet stuff was published, a couple of years later, there wasn't much to do with machine learning because again, you don't have compute, so you don't have auto grad back then. So what are you really going to do? Well, people invented new methods called kernel methods. A kernel is essentially a function class that takes in some inputs, produces some pairwise outputs. So that's essentially all you want to know. This ties in with support vector machines where your data is projected into a certain space and then you try to shatter this data in this space. And that is your sort of classification problem where you learn a decision boundary in the space that you project the data to. But anyway, that has to do with picking a certain kernel that you think will work well on this data. That kernel creates a convex optimization problems. And there are a lot of theorems that have to do with convex optimization that were applied in this field, and it worked reasonably well. But and I don't know why he's written 2000, but anyway, the point was after kernels, people started to realize that, okay, when you want to work with images, there might be certain geometry that we can actually exploit. You can extract certain features, you can hand engineer. Feature engineering was a big deal where people actually extracted features from images by hand, design, in the sense design feature extractors. And even though these resulted in certain non-convex optimization problems, there were still ways in which people created solvable, created solutions for them. And under certain assumptions, yeah, these methods work very well. And so this is an idea of feature engineering, how you create features from images by hand. So for instance, if you want to detect a certain curve, then you place a certain number of weights on that. Oh no, mind not getting into that detail. What I will say is there is a difference between like you can't sit and create an infinite number of features by hand. There is a certain physical limit to creating features. Secondly, there is a certain intuition that you apply in order to do feature engineering. You might be missing things. You might not know all of the necessary features that you want to capture, but for the time being, it worked. People could detect enough sufficient number of features to do certain object recognition. Um, and then they just dumped it into this SVM class of methods and created certain outputs. And it worked reasonably well. So in the beginning, we had yeah, this is just showing you the diagram is just showing you the progress of hardware in time. And what I was getting at was saying that hardware originally started linearly increasing, but then in the 2010s to 20s era, there was some this was data. So hardware, there was a massive bump in hardware, where about a 10,000x bump in hardware, and similarly big data became a thing. And I'm not going to harp on that because you already know all of this stuff. What I really want to give you the intuition for is in the 90s, there were deep nets, then there were kernel methods, and then we went back to the era of deep nets, mainly because of this data and this hardware boom. Cool. So in the 2010s, someone came up with this. I think some folks at Stanford came up with the ImageNet challenge, where they said, okay, we have a much bigger data set than MNIST, so we can do more things now. Like, this is a more general sort of data set moving towards more general object detection methods. Because it has 1,000 classes, it has far greater number of examples. Plus, the examples are now color images. So there are 3 channels, and the images are of a much higher definition, which means bigger size. Anyway, so you see that the field is moving accordingly. The architectures are evolving, and really, when people started noticing AlexNet is when AlexNet started doing really well, and it won the ImageNet challenge in 2012. So then people went back and said, okay, wait, what was AlexNet really doing? Well, it's essentially a deeper and bigger LeNet, right? So it's the same kind of architecture. You put your dense layers on top, make the dense layers bigger, make the convolution layers deeper. And that's about it. But it had these ideas inside it that had we've seen dropout before. We've seen ReLUs, and we've seen what max pooling is. So this idea of initially learning some lower level features, combining them to learn higher level features, and reducing the granularity at which you learn the features, that really shone. And people started looking at, okay, we can actually build deeper networks for computer vision. And so the paradigm shift was from these manually hand engineered features and these custom methods being applied to going for automated features learned by these filters in a CNN, and saying, well, give your data to the network, let the network learn the stuff for you. So yeah, that's really what changed. And if you want to spend a bit of time looking at the difference in these the convolution sizes for LeNet versus AlexNet, AlexNet actually had bigger filters, and it sort of made sense at the time. Again, when I say make sense, like, a lot of this might not make sense when people were building it. It worked, and then people came up with explanations for it. But on the other hand, and this I learned while preparing for this lecture, a lot of it actually had cool experiments designed to highlight it for the people who are building it. And then they said, look, our experiments work, so clearly there is something here. So we'll get exactly into that. Let me know if there is a lot of background noise for me. Cool. So again, bigger kernel sizes, a larger pool size. So you're aggregating because you have bigger feature maps, you want to aggregate across bigger feature maps, so you have larger pool sizes. So that sort of ties in with each other. But that was what they got at. And you need bigger convolution sizes because now if you have higher definition images, then you want to aggregate across these larger or more complex complex images. So your object might be spread out across a larger number of pixels than if it was just a 32 cross 32 image. So there is some sort of intuition behind, if you go for higher definition images, kernel sizes should be bigger, and we'll start seeing some interesting patterns as they emerge. So another thing they did was they add more convolutional layers. They're like, okay, we want to make the network deeper. Again, the intuition here is like, okay, there are some lower level features and you need to give it enough layers to get to the higher level features. And finally, more output channels, because you want to split your well, yeah, the kernel, sorry, I should say filters and not kernels, because kernels might be confusing for some people. um, yeah, that's a great question actually. Why did they call it kernel despite the existence of kernels that really do something else? um, Anyway, I guess that is a question I will have to think about and post the answer to. So kernel methods is different from convolutional kernels and convolutional filters. So in convolutional neural networks, kernel implies filter. I may have mentioned that implicitly without clarifying. That is my bad. And thank you so much for posting it on the chat. So filters. Let's say filters. So three additional convolutional layers, more output channels again, because you have more sort just more data to work with. Let's go with that. You have image. This was designed for the ImageNet challenge. So there's 1,000 classes of output. You want to predict the probabilities, the class probabilities, and then take a threshold and pick the largest, pick the best class that is predicted. And the hidden layer size is dramatically increased, which also increases the number of parameters, because remember that a hidden layer has a parameter per neuron, right? Weights and biases. So yeah, that's about it. Um, like we said before, just add a dropout, change the activation function from sigmoid to ReLU. Remember that sigmoid to ReLU was the vanishing gradient problem, where we discussed a sigmoid function towards both ends. I should actually draw here, but never mind. Towards the end, the gradient really isn't much, whereas in the middle, there is a lot of gradient. So the ReLU, we address that. There is a kink, sure, but about the kink, and this is a question that someone asked in another lecture I was watching. Um, the idea behind how gradients are actually implemented are apparently subgradients. And so the kink issue, where at the kink, this gradient is zero because it is a sharp edge, that might not be as much of an issue because of the numerical implementations that deal with it. So cool question. But I just wanted to mention that. Anyway, another trick mentioned here is data augmentation, where you want to create different versions of the same data, either rotated or translated or cropped in different ways. But the motivation being, like, when you look at an image, even if it's half a cat, you're still going to recognize it as a cat. So if your network should be able to do the same. If it's a rotated cat, you're still going to recognize it as a cat. So your network should be able to do the same. So that's what really stimulated the idea, intuition behind data augmentation, that your network should not change if it's a different sort of picture. How are we doing on time? I am almost an hour in, which is not great. We should speed up a little bit. Not, I mean, I'm not going to spend a lot of time on this because this is fairly straightforward, but you should look this up, because in the sense of comparing the number of parameters and the flops or floating point operations per second. Floating point operations per second is the required compute for operating on the network, training the networks. Fair. And the corresponding increases was really a lot, like 250 times an increase in flops is massive, and it definitely requires computational advancements. But more on that later. Let's get back to the next kind of architecture. So after AlexNet really worked well, and people started realizing that deep neural network. So I think AlexNet was the deep learning revolution, because it was the first sort of coming of age moment where people started noticing, okay, deeper might work, after like years of not actually focusing on deep neural networks. So that was super important as a paradigm shift in approaching these big data challenges. Cool. So with VGG, again, the intuition is let's go deeper. So if AlexNet was deeper and bigger than LeNet to get a good performance, can VGG be even bigger and even deeper to get more performance? The only problem that comes with going more deep, or yeah, the real problem with going more deep is it adds parameters, and adding parameters means it needs compute. It's expensive. So what they came up with is they just grouped these convolutions into blocks, and each block is essentially doing something um, um, in a repetitive fashion. So it goes from um, um, deeper and narrow. Yeah, I think it goes for a narrower idea, and it the so you divide the problem into sub problems where you design these blocks and then repeat the blocks to get this kind of architecture. That was the intuition here, if I remember correctly. Cool. What I don't want to spend time on is this thing. Well, you said this, and I'm going to get to a problem of this. Like so far, we keep talking about number of parameters, and the real problem that we run into is these dense layers, where the dense layers really are parameter hungry. So if you have a lot of dense layers, you're going to have to optimize a lot of these parameters. But essentially, nothing too important to take away here. The challenge, like we said, if you go even bigger and deeper than AlexNet, you're going to have even more parameters and memory footprint. So this plot basically the size of the circle. So the circles indicate the kind of architectures. So the pink ones circled here are basically a class of VGG architectures with minor things varying internally, but like the number of blocks used in this architecture. But the size of the circle, which you should really care about, indicates the memory footprint, and that is a big deal because if well, this is a ratio. If I am being more precise, it's the accuracy versus the computation to accuracy ratio, which means for the same accuracy, you're really occupying a much larger, you're taking more computation, which is a problem because you need enough of an accuracy improvement to justify throwing that much compute at it. And so that's the comparison, that AlexNet has a much smaller memory footprint than the size of this pink circle, which is the class of VGG model. And so somehow we need to reduce these number of parameters and reduce the memory footprint. So someone introduced this idea of network in network. And what network in network says is, look, the problem is coming from these last layers, right? The real challenge of these higher number of parameters is coming because in convolution layers, there is weight sharing. So that dramatically reduces the number of unique parameters needed to be learned. But in these fully connected layers, there is no weight sharing. Like each of these has their own weights. And so we have a problem here. So how about, and this is just a comparison of the weights in the last layers. 48,000 weights in LeNet, 26 million weights in AlexNet, and 102 million weights in VGG, which is a really big deal. So what people started doing, again, not important, breaking the curse of the last layer. So the idea behind this, and I've mentioned this once before, I don't know if you remember, was the idea of 1x1 convolutions. So 1x1 convolutions essentially do the same thing as an MLP because it doesn't reduce the output size. It projects it to the same size. So it's essentially like a fully connected network, but like projecting it to the same dimension. But it dramatically reduces the number of parameters needed. And you can always do pooling at the end to reduce the size to whatever you want to. So what they said was, let's move these things. Let's remove the end of this, which has this densely connected layers, the end of the architecture, which has these densely connected layers. Instead, like move these internally, add these layers of 1x1 convolution. So in a sense, we're still allowing for the expressivity, but reducing the number of parameters. And that was this simple idea that created the set of architectures called network and network. Unsurprising, not unsurprisingly, but they don't necessarily work of like as well. It wasn't as much of a accuracy improvement, but it was definitely a very cool innovation in terms of here is how you can dramatically reduce the number of parameters. So yeah, that's what this is saying. Essentially, your 1x1 convolutions are used to create a network in network block. You still have your hyperparameters, you still have some weights you learn for the kernel, but it shares the same number of output channels as a layer and essentially acts as a dense layer. So instead of these three dense layers that you need to dump on top of this VGG architecture, now you suddenly with the network in network block, you just need a global average pooling. So a final layer pooling your inputs or inputs up to that point into the number of classes that you want to do the prediction on, and that's the only layer you need in the end because you added these 1x1 network and network convolution layers internally. I think that's all I want to say about this. Same idea for AlexNet. And that's the summary I want to give you for that. Before I get into the Inception. So the Inception and ResNet are really the two cool architectures that you'll even today you will use for whatever purposes in image related problems. And with that, we're getting to more recent times, and Inception was basically this idea that okay, there are different kinds of convolutions that exist in all of these architectures that we've had before. There are 1x1 convolutions, there are 3x3 convolutions, there are 5x5, there is max pooling, then and network came up with these ideas of multiple 1x1 convolutions. So what sorts of combinations? So now these folks at Google, I believe, had this field of like, here are these components and our goal is to figure out the optimal way to combine this. And what they simply did was, why choose? Just pick all of them, create this architecture or this block to be precise. Like we discussed, there are these blocks, and then repeating these blocks creates these architectures, and different numbers of repetitions correspond to different types in the different items in this class of architectures. So they said, let's just create this architecture with all of these kinds of convolutions, and then in the end, we put all of these together. So we combine the channels or concatenate all of these separate inputs, but we apply these convolutions to the same input. And so that's exactly what they did. This constitutes a certain inception block. And again, the motivation is that all of these channels have separate capacities. So individually, they are slightly lower channel size because you remember in the previous blocks, there were just one, there's a convolution per layer inside the block. But now you're splitting these into different channels. And so initially, all the channels went to that one layer. Now you're splitting channels across layers. And in a sense, you're expanding the capacity because in a sense, you're increasing the expressivity because you're applying different kinds of convolutions. You're learning at different levels. And it works well. Inception blocks have fewer parameters because of this channel-wise split. Instead of just a 5x5 convolution applied to everything, you have 3x3, 1x1, 5x5, all of them. Memory and compute efficiency, and that's useful because then you can train it on more data, just train it for longer. And so we described, so far we spoke about this one block and creating different combinations using this one block creates this entire architecture of GoogleNet. But really, like these different classes or candidates in this class of inception models, they tweak different things in these blocks and add different blocks at different stages. So let's take a look at a couple of stages, like what are they doing at these stages and why does this make sense? So stages 1 and 2, you create a smaller kernel size and output channels due to you have a lot of layers. Again, you don't want to blow up the parameters. The idea was to reduce the number of parameters, so you keep your kernel smaller. You have this is, so you want to read this from bottom to top, where the image goes in at the bottom, you pass it through some layers, and the output comes out at top. So it's just comparing to AlexNet. It reduces the kernel size. So remember that AlexNet, from LeNet, AlexNet increased the kernel size. Now from AlexNet going to GoogleNet, we're reducing the kernel size. Because we're saying that, hey, this is going to learn in terms of the depth of layers. We have a much larger depth. So maybe we want to create smaller kernels and then increasingly internally create representations that you learn from. Stage 3, what's going on here? So takeaway here is you realize that there is an increased number of output channels. So inside the network, you're blowing up your data. You're saying, I want to create a more expressive representation before combining it back down into whatever I'm predicting. So that's the idea here. Your input comes in from the previous stages 1 and 2. You blow up the number of channels slowly, and then end up with an increased number of channels that have passed through all of these different kind of convolutions and been concatenated. Cool. And I don't want to say much about stage 4 and 5. It's more of like combining blocks. Doesn't seem like I want to say anything. There is batch normalization, but we will get to batch normalization, I think, in a couple of slides. Anyway, and we will also get to residual connections. But again, the motivation here is these blocks modified in different ways, combined in different ways. And one of the ways in which they were modified, at least one of the interesting ways, we get to now, where they say, okay, this is the kind of inception block that we want to create. So in a 5x5 convolution, you have 5x5 parameters, which is 25, right? And instead, if I replace this with 3x3 convolutional layers, this reduces my number of parameters by a lot, because you're doing this repetitively across multiple blocks. And so you're at a small cost of creating a slightly smaller filter, you're getting a relatively higher reduction in number of parameters. And so they said, well, we can also do this in a better way, like just 1x7 convolutions and 7x1 convolutions in stage 4. And so again, the intuition here, all I'm trying to get at is like, this is how these architectures evolved, because people thought of these things, and what you really want to understand is just what they thought of. And so what is a 1x7 convolution? It is this 1 row and 7 columns, and that's the convolution that you move across your data. I should really draw here. Wait a second. What's the meeting ID? Cool. So what I was simply trying to say is that this is a 1x7 convolution. This is how a 7x1 convolution might look. So can someone tell me why you might want a convolution like this? The first one, 1x7. You can post it in chat or unmute yourself and talk. Okay. Sweep through the image. Yes, you're right that you want to sweep through the image, but a convolution is supposed to detect something, right? So what might you want to detect with such a convolution?
Swapnil, is
Edges
it to
maybe.
filter
Yeah, go ahead.
horizontal and vertical edges? Like that's the only
Exactly
reason.
that. So
Yeah.
there might be some features that are horizontally present, and so you just want to track some, use some horizontal filters, sweep through the image, and detect where that detect if that feature is actually present in the image or in the representation of the image at that layer. Because remember, this is a block, so there already has been stuff done before, and then at some point you want to detect this vertical horizontal feature. But that's exactly the idea, that yes, we do want this horizontal feature detection, we want this vertical feature detection. In the end, you want to end up with a reasonable shape. So that is the idea behind this, and in doing this you also reduce the number of parameters by you don't really reduce it, but it's at a very low cost that you can actually detect these kinds of features. I say you don't reduce it because there are still like 7 plus 7 plus 7 plus 7, and remember we had the 5 cross 5 before, so these are 28 parameters and we had 25 before. But at the same time, you're increasing the expressivity compared to one layer of convolution or 5 cross 5 convolution. You're adding 4 layers of 7 cross 1. So again, a lot of this is playing around with architectures. Why 7, why not 8? Why 7, why not 6? I don't think there is an answer to that. It just worked. And typically you don't have an even number of convolutions. So anyway, getting back to what we're talking about and going for similar kinds of ideas, except now splitting across channels, right? So from a 3 cross 3 convolution, you go to 3 cross 1 and 1 cross 3, and then you combine it back. So the idea, and we'll get back to this idea of like splitting across channels, splitting channels, where when we'll get to like ResNet to ResNext, where you split by channels. But for now, again, the intuition is do the same thing but better. Give it more expressivity. Cool. So Inception v3 seemed to dramatically not dramatically reduce, but at least reduce the memory footprint and do better in terms of efficiency compared to the other class of Inception architectures that we saw. So maybe maybe there is something to this splitting of channels and reducing parameters and thinking of these increased but smaller number of convolutions. And with that, I take a brief detour into what exactly is batch norm. So Inception used this idea of batch norm, and I briefly mentioned it but didn't get into it. I said get into it after a bit. Well, the idea is in going across this entire deep neural network, what there are a lot of changes that happen internally. Like there is a lot of transformation, and in some sense we want there to be a stable transformation. So you're not like in the last layer and the first layer, you want some relationships to be preserved. Otherwise you might as well just be transforming random numbers, right? And the intuition is that sure, as you increase the number of layers, you increase the number of transformations, you might end up much different from where you originally started out. And so in order to sort of stabilize this, the same way that we normalize our data to avoid these high variance effects, you use batch normalization internally to reduce these high variance effects of your data being transformed. That seemed to be the motivation for batch norm. As it turned out, that wasn't exactly it, but we'll get to that. So first, someone had this intuition that last layer might be doing something very different from first layer, and we're back propagating everything backwards with the assumption that it has some stable pattern. So like we really want to ensure that there is a pattern being preserved across all of these transformations, right? Um, so what we do was we fix a certain mean and variance of this data, and we adjust it. We use some hyper parameters for this batch norm layer that basically adds some stability after every couple of layers or wherever you put this layer to your data transformations. And so someone said that we're doing this transformation, but um, at an internal representation, you are adding these hyperparameters to figure out how much uh, um, you want to transform or normalize your batch. Yeah, I guess that's all I want to say. But as it turns out, this was just the original motivation, but it didn't actually work that way. Like when people tried to if this reduces this covariate shift, and by covariate shift you mean your test data and your training data is very different. That was where the intuition comes from. And what we said here was this first layer and last layer has sort of different representation, very different representations of data. So in a general sense, covariate shift is just that your covariates are shifting very far away from where they were originally. That sort of intuition. Like you learn your homeworks from a fifth standard math textbook, and suddenly your exam comes from the 12th grade math textbook. So that's in a sense covariate shift. It's still math, but it's just much harder math. So that is just giving you an example of this phenomenon. And so they realized that this doesn't really address that problem. Instead, you're basically, what batchnom is doing is you're adding some noise per batch. And on average, because of this noise addition, you are adding some randomness. And so it is doing something similar to dropout, where you're saying, I'm going to drop out stuff at random so that I don't overfit on my training data. So that seemed to be what batchnom ended up doing. So there was some intuition, and this is a great example of how that intuition was not actually what was happening. And some people designed more experiments to test and figure that out. But the point is, regardless of intuition, batchnom works, as with a lot of machine learning. And so we use batch normalization on a per channel basis. Effectively, in order to regularize, avoid overfitting, similar to other stuff you do to avoid overfitting and dropout. Cool. So your batch size or mini batch sizes really affect batch norm, because now you're using those batches to compute the normalization, right? So that is important for you to consider when you're adding batch norm. Like if you have too many things in a batch, your normalization isn't going to do anything, because on average your noise is probably not going to affect your data. So you want to keep your batch sizes reasonable and then add batch norm and play around with that. With that, we come to the end of most of the architectures except for one. And for that one, I'm actually going to switch to a different set of slides because it was just super interesting. So Kaiming here, I think, was the original first author on the paper called Deep Residual Network. So after inception, there was this series of architectures that really took over. And this is what I used in my last machine learning project in order for image detection. So it is really state of the art, or somewhat state of the art, because there have been architectures that do a little better than that. But yeah, anyway, it is the same class of architecture. That's what I meant. So with that, let's switch to Kaiming slides. And that here, stop sharing for a second. Can I increase to full screen? View. Now mind we can look at it like this. Let's share again. Cool. So the reason ResNets really came about were because they actually got first place in a bunch of different tracks in a competition. When I say came about, I mean became popular. So, and that is like a massive jump from even this inception style of architecture is already doing really well. And so it's not just that, it's actually that they did much better than even the second place. So these double digit improvements these days, if you work on these challenges, even if you get like 1% improvement, you can publish a state of the art paper. So doing 16% better is really like a big deal. And so what we're going to examine is, and I found a video of this author from 2015 with really shitty audio on the internet. So I can point you to that if you're interested. But what I try to do is take away his stories of like what we thought networks were doing, how we designed our experiments, what we found, and how that resulted in this architecture. So let's get into Did I not switch slides? Yep. Okay, cool. So from 2010 to 2014, you can see these architectures that you've studied that are performing really well in this particular image classification challenge, where AlexNet comes in, VGG comes in, GoogleNet features, and now ResNet does something that reduces this error dramatically. So from 22 layers, we jump to 152 layers. And so they're really exploiting this let's go deeper. And again, different challenge, same sort of idea. ResNet has 101 layers. So again, these are different versions of ResNet. There's ResNet 152, there's ResNet 101, working on different challenges. So clearly they tried out architectures, picked the one that went best. But it belongs to the same class of models. Anyway, AlexNet, we saw it is deeper than LeNet. VGG, we saw it's a bit deeper than AlexNet. We saw the Inception class of architectures. It's even deeper. And then you look at ResNet in comparison to this, it really puts things into perspective. This is massively deep. And like it's really mind blowing how deep they went. And so ResNet 152 has a lot of layers. And so the question they started asking is learning better network. They started when they were doing this. The question they asked when they started this research is learning better networks as simple as stacking more layers? Because that's what these diagrams seem to tell you, right? Like if you're just going deeper and learning before ResNet, if you're going deeper, is that just better? And so is the solution to deep learning to throw more compute, add more layers? That's it. And as it turns out, that is not the case, because if you take these small problems and they design these problems where for the same architecture, you just add more layers and you solve the same problem. As it turns out, in green, you see like a 20 layer network, and in red, you see a 56 layer network. In terms of both training error and test error, the 56 layer network belonging to the same class of architectures was worse than the 20 layer network. So it's not that simple. So because it turns out 56 layer network has a higher training and test error. So, and this simply stacking of layers really doesn't solve the problem, which is very weird, right? Because if you think about it, if you compare the two networks on the left and the right, the one on the right has the same layers as the left, and then it has some additional components. And if you set the weights of these additional components to 1, it is doing exactly the same. Like not set the weights to 1, but if you create an identity transformation with these additional layers, which is possible, right? It is doing the same thing as the shallow model. It is technically a super set of models. Adding more layers doesn't mean you reduce capacity. In theory, it means you increase capacity, which means adding more layers to the same network will still be able to learn that same network. But it does not, because clearly these plots show that for the same architecture, adding more layers results in worse performance. So that means we have some difficulties in optimization, and you can't necessarily find the same solution when you're going deeper and deeper. So what can you do that allows you to capture this identity mapping for deeper networks? Is this question fair to everyone? Like, are there any doubts about this question? Please feel free to unmute and ask.
Could you explain what do you mean by identity mapping?
Gotcha. Identity mapping is just a transform that maps X to X, right? So here you compare this arrow. This arrow just indicates that there is no change to this 3x3 convolution before going into this red 3x3 convolution, right?
Correct.
I'm saying if instead of that arrow, I add these 4 layers in the middle, but these layers don't actually do anything. They still just identity map the input. So if X goes in, X comes out. This is possible, right? With a neural network, you can transform it by setting the weights to a certain set of values, you can transform it into an identity mapping where the network is not doing anything, right?
Yes.
There are no pooling layers in the middle node, so the dimensionality is not changed. There are just convolutional layers.
Okay, yeah, I got your point. But why is
So
that needed then?
right. So the reason I said that is, so the question they started with asking is this, right? Is learning better networks as simple as adding more layers? So if you add two layers to this network, you still have this entire network that you can learn with two more layers in theory, correct?
Yeah.
If those two layers are set to identity maps, it reduces to this original network. Is this fair?
Yes.
So the question they asked is, why can't we learn that? Like, why is this network doing worse than this network? Because that is what these plots are showing. That deeper networks are doing worse than the shallower networks on the same training data.
Okay. Yeah. Now I got your point.
Yeah, which was really surprising to them. But turns out that at least this is the intuition they came up with, that if you add more layers, your optimizer just doesn't manage to handle it. It runs into some local optima, stops there, and doesn't get to the previous optima. Previous optima being the shallow network optima. So just adding layers does not solve the problem. And the solution they want to allow for is to at least learn the shallow network from this deep network, so that you're not losing out on simpler solutions just by adding more complex solvers. Fair?
Yeah. Fair enough.
Can you tell me how you can add a simple way to add an identity map in place of this layer?
Uh,
You want to allow for both an identity map and this layer.
yeah. I can't think of anything. Uh, like you can apply identity transformation for
In a
this.
sense, that is like, yeah, go ahead.
Yeah. I,
So if I tell you I want to create, if I have one exit out of a room and I tell you I want to create another exit out of the room, in the first exit you go out, you will have to walk on fire. The other exit, I want to say you just have to walk on the same stone. How do you do that? You have one door out of the room. Outside the door are hot rocks. You want to get out of the room, um, but you have to create a way that doesn't involve you walking on the hot rocks. What do you do?
uh, okay. I create another, like, okay, wait.
Create
Hmm,
another.
yeah, exit sort of.
Exactly that is the solution. That is how they built Resnet. They created another exit path with nothing, which is this thing. So if again, I'll get to that later. Let's just see this. They basically, this arrow you see here, that is the exit path they created, saying, well, it's just an identity map, then we can just create another connection. And if the network feels that this allows the network to fit a new function, just learn zero weights for this. So close off this door and instead just take this door. Is that fair?
Okay, yeah,
Right. So
yeah,
now let's get into the math. What they're saying is, if originally if you're originally trying to learn this function h of x, and there are two layers in the middle, but we want to allow to learn an identity mapping, um, which means h of x, if we say this is equal to some other function f of x plus x, right? Then we can just create this separate mapping directly here and then allow these weights to go to zero. And this
okay.
was the simple and mind-blowingly awesome idea that resulted in this class of architectures called ResNet. And again, the point I did all this was to tell you that, look, people created these tiny experiments, and this doesn't have to be millions of layers. You can create this with 5-layer and 7-layer networks. Train it on your local machine and try it out. So when you think of projects in machine learning, these are the kinds of projects you want to think of. I'll talk about, like, at the end of the lecture, remind me to talk about another experiment um, by someone else, which was recently published in the Journal of Machine Learning Research, which is like probably the best venue, most relevant venue in my field that I can publish at. And the idea is so simple that you and I can sit and discuss it. Like it doesn't require any math. It doesn't require any additional knowledge or whatever. But anyway, I'll get to that at the end of the lecture. So remind me about that. But for now, you follow that this is the simplest idea that allows you to still capture the shallower network, even in deeper networks. And so this is called a residual mapping with respect to identity. Um, I I don't think I have anything more to say. With that, they showed that this was actually done with a bunch of other things also. So uh, there are already people solving residual subproblems. People just didn't notice that these were very similar to each other. And so that's why this skip connections, I think it's called skip connections, I'm not sure. But skip connections and ResNets came about. And then they decided, okay, now we can keep adding layers, more and more layers, because now in the worst case, the network just learns zero weights and eliminates half of itself. So yeah, that's very simple. The same stuff, more or less the same stuff that VGG did. They didn't do anything specific other than that, and they just trained this from scratch, used the usual stuff, got their cool results. Nothing major to do here. Um, what do I want to say about this? Not much. I just wanted to give you the intuition for ResNets, and then because I have just 15 minutes left, I want to jump into
Swapnil,
application. Yeah.
yeah, sorry to interrupt you, but there
No, no,
were
go ahead.
dotted arrows in the bigger diagram. I just wanted to know what are they. So if you
Yeah,
look,
that's a great that's a great question. I'm not very sure what the dotted arrow is. I should be sure because I've used ResNets, but I didn't actually look through the architecture to think of what that dotted arrow could be. I'm pretty sure it has to do with channel sizes, because yeah, I think so. Because this is I don't think I want to say anything about that. This is
Swapnil, I think you're right. It's that only. That's a different type of transformation to the skip connection, so that the channels are aligned.
I think one is
uh,
identity mapping and other is like passing through convolutions here. So that is like two different types of like residual connections. Dotted arrows I think represent the convolution connections like mapping.
okay.
There
Well,
were two
you have
types
a
of
bunch of answers. You can
yeah.
figure that out. But that's a great question. Sorry, I didn't have the answer ready for you. Cool. So with that, this idea of ResNets came about, and ResNets are really popular. ResNet 50, ResNet 101, ResNet 152 are still things people use for image feature extraction, and fine tuning for multiple applications in different areas. But I want to get back to, I think I'll have to reshare. Let's first. Cool. So one of the things I should say is ResNet is not like I mean, there have been architectures after ResNet, obviously. ResNet was, I think, 2-3 years ago, um, if not more. So in 2016, ResNext came out, where they said, okay, here is ResNet, and all we're doing is splitting across channels. So instead of having what is this, 64 channels? This should be two. Not sure what the dimensionality split is, but bottom line being they split the same sort of transform across multiple sub channels, I should say. And the reason is, again, they claim to increase expressivity, and by splitting this across channels, they reduce the number of parameters required to be learned. So marginal reduction in number of parameters, but increase in capacity. So why not do it? And I think ResNext, yeah, the CI by B is essentially indicating channel input and channel outputs, which are the dimension of the input, dimension of the output in terms of channels divided across B channels. And diagrammatically, you might want to see this. This is showing you that, okay, the same stuff, the same architecture replicated across multiple sub channels, across sub channels, I should say, not multiple sub channels, but yeah, same idea. I don't think I want to say anything more about that. We have, yeah, I mean, the idea of splitting across channels, we did see where we, let's go back and show you this stuff. No, this stuff. Yes. Actually, even better would be the stuff where you're splitting across channels, like these arrows go to both of them and then they are ultimately concatenated. So same intuition, except now done across all of these different blocks in the ResNet. I feel like we've discussed that enough, but short note on res next was necessary because again, like you have to think of how to optimize this already optimal architecture. Well, anything you can do to reduce parameters and increase capacity seems to be a reasonable way to go. And that is where I will end the architecture section of today's lecture and get to applications. There are just to be clear, there have been other architectures that have come out. ShuffleNet, again, I just look at the diagram here. It might make things obvious where we set these identity mappings, but now we have this multi-level identity mapping or whatever you want to call it. That seemed to work out for them. However, ResNet trained correctly does seem to work better than DenseNet. I think Smola mentioned that in his lecture. So again, like people just tried out these different ideas. There was an idea of attention where, well, let's not get into attention. Actually, we'll do that next time. There was this idea of mixing channels. So while this sub-channel idea came about, what about like combining different sub-channels and playing around with that, or shuffling the order of different channels? Anyway, those things seem to work out efficiently for MobileNet. Seem to, I guess, computationally work out. And I don't think I want to get into this. I want to really jump into applications. So we will look at slides by Neela Murray, who is now at Facebook AI Research, I believe, that talks about a bunch of different, like I spoke to you about applications of computer vision, but now I really want to dive, sharing is paused. Sorry about that. Start sharing. I spoke to you about applications in computer vision, but I want to show you a bunch of them and what sorts of in detail. That's it. So with 20 minutes on the clock, let's get into this. The first thing she talks about is ResNet. We've already seen this, so I'm going to skip this. Object detection is this super simple idea that most of you already know. There is an image, there are certain objects in the image. The goal of your, the problem you have on hand is to create a bounding box around these sections of images in which you believe a certain object is present. And if you think a bit deeper, like how do you really go about this? Well, here is a popular architecture of YOLO, which is a super good object detection network. There are actually YOLO V1, V2, V3. So it is a good class of models that really worked out well. But not going to get into the details of that. Instead, I want to talk about this problem. So if you think about this, when you want to detect objects, what you're essentially doing is you're placing a grid over this object, over this image, and you're saying within this small, can you identify the small boxes that correspond to an object? And then when you draw the diagonal, you just place a box around it. That's how you get the square. You basically want to see the class probabilities for each tiny box and which is the most likely object in that tiny box. And then combining a bunch of tiny boxes, you create this big box or bounding box that you output. Yeah, so just thinking about it internally, you are creating many small tensorized representations of your image. Tensor because 3 channels times height times width. It's no longer a matrix, it's now a tensor. and you want class probabilities for each of these items in the tensor. Cool. If there is any doubt, I should have started with this, but if there is any doubt ever in any lecture, just pause me and ask me questions. I think you already know that, but just repeating that. Cool. Taking this to the extreme, you have instance level segmentation. So now if you think about this grid as well, why do I need to place a larger grid? I can just do this pixel wise. Sure, yes, you can predict class probabilities pixel wise and then pick the set of pixels that accurately represent a certain class. And then accordingly, you have instance level segmentation. Instance level segmentation can be done using this popular method mask RCNN. Mask RCNN, I don't think I want to say a lot about that. Just giving you these popular examples that you will find in practice. And another reason that I mention these architectures is because they are already available pre-trained in existing libraries like PyTorch, if I remember correctly. I know ResNet is available. I think YOLO is either separately or available in Torch. I know Mask RCNN might be available, but I'm not sure. Anyway, getting to more applications, there is image matching and retrieval, where given a query image, you want to find similar images in large database. This is how Google image search likely works. There is another popular method. There is a popular method that is used for deep image retrieval. What you want to take away is the intuition for this loss function. So someone sat down and thought about this, and they said, well, okay, so typically in training, what happens is we have a label and we have an input data. And the goal is to create this input data that is similar to this label, that is able to predict this label. And in image comparison, I want to compare two images and say if this image is close to this other image. And so combining, adding on another idea or taking the converse of this, I want to take two different classes and I want to ensure that the intra-class distance is maximized. Sorry, the inter-class distance is maximized. So between two different classes, the distance is maximized, but the intra-class difference is minimized. So a relevant image is brought closer, but an irrelevant image is pushed further away from this query. So that combining this gives us this triplet loss where you have positive example, negative example, query. And you want to bring query closer to positive, but push query away from negative. And this is like a super important class of losses because there's been a lot of work done on triplet losses in terms of both theoretical and practical applications. But this, now we start getting into what Smola said when he meant if it is trained correctly. So optimizing improvements and loss functions are like, once you stop innovating on architectures, you can also think about innovating on these kinds of things. Cool. So Jess says for the task of object detection, YOLO and RCNNs are two different classes of models available. Siamese networks seem very popular for facial recognition as well. Yeah. Cool. So with that, we can get into the last couple of applications and then close for the day. Video action activity recognition is this where now, if you think about this compared to images, in videos you have a sequence of images, right? So there is a certain relationship between images that are close together, and that relationship grows weaker as you grow as the distance between images grows further. So a bunch of different recent ways, and I don't think these are in the slides, but a bunch of recent approaches is to cluster, like build a graph of relationships. Like here is a ball, here is a man, relationship between ball and man is holding, because man is holding the ball. And then there is a ball that across the frames, you can track this ball going somewhere. You can track this man's hand moving somewhere, and then you can build up a relationship between those things. But those things are being done using graph neural networks, which is another super cool set of techniques. One of my research areas. But anyway, here, let's, again, I don't want to get into the specific ideas, but two important things: this sequence and relationships maintained across a sequence. That brings us to LSTM networks, which we will look at. But before that, that brings us to this idea of three-dimensional convolutions. So convolutions are not only in height and width of the image, but now in a sequence of images. So another dimension is added to the convolution where you're detecting this object across multiple frames, if you want to say that. Yeah, I think that's fair. And that allows you to build these filters where you detect motion in a direction and like those kinds of things, just because you have videos now. But it's also super expensive. You can imagine the parameters blowing up very easily if you create very large 3D convolutions. So that's all I want to say. I think there is a lot more to be said, but I don't really want to confuse you with that. Like this idea of sequences is enough for you to go on and explore on along that front. There is, I think, two last ideas that I want to get into. Image generation, where the idea is you want to take in a certain you want to take in some random input, and you want to transform that input, like chain a series of transformations in order to produce a certain output that is close to what you want. So in this case, you want to generate an image that is similar to the image that you have in hand. And this is typically done using a class of models called generative networks. Generative models, as the title states, are capable of generating images. I think it started with VAEs. I'm not sure if there were things before VAEs. VAEs are variational autoencoders. So what variational autoencoders do is first they blow the data down to a certain dimensionality and then re-blow it up to the original image. So the goal is to reconstruct the original image from this space. And in the end, what you want to do is just take a random point in the space and reconstruct images that are similar to the images you have in hand. That is how you can use VAs to generate images. But that the real goal is like when you're blowing this image down or compressing it to the space, that space has to mean something, because otherwise you're not really doing anything special. So this space is probably like the space of images. So you can, if you sample 2 points that are very close by in the space, it's likely that you'll get 2 points that mean the same thing, like two whales and so on and so forth. But again, I went too deep into that example. There are different kinds of generative models. Part of it is used in generative adversarial networks, where now you have a police and you have a thief, where the thief tries to fake these images. The police tries to catch which images are faked, and the goal is to push the policeman to make the thief better. And in the end, you care about the thief because the best thief in the world can generate any possible image, and that is really useful. And that is where all you see all of these. Oh, we can use GANs to generate faces of people that don't exist. How is that possible? Well, because we trained the thief to create fake faces really, really well, and now it can actually create faces that don't exist. Because it's not in the training data. Like if the training data is all the people in the world, your thief can create more faces than is even possible in the training data. I think that's enough to be said about that. The takeaway, I don't think there is stuff I want to say about this. I think there was stuff I wanted to say about something else. Yeah, okay. So image translation, this is where it comes. Okay. So in image translation, the idea is, as you can see in these examples, convert an image from one particular label to another, I guess. And so this also ties in with style transfer. So if you have a field and you want to convert it to a certain style of an artist's style, then you want to maintain some aspects of the image and change this style. So you still want flowers, red flowers, to be there in the image, but you want to overlay a different style. Or all of these filters that you see, well, not all these filters, but these style filters, some of them I hope you are aware of on on these Snapchat type apps, where you change your, well, not overlay stuff on your face, but change the entire, again, the style transfer is all I'm going to say. I'm bad at describing it, but hopefully you follow. So the intuition I wanted to give you in this image, these kinds of image translation tasks, is you don't want to blow this down to a really small space, because that means you're losing some information. And by blow this down, I mean, I'm still talking about these generative models, right? So what Neela Murray says here, and which struck me as like seemed very important, is because this channel size does not drop down to a lot by a lot. You're still keeping most of the original data, but you're reducing it to the bare minimum, and then you're adding on this new style and like converting it via a transformer to whatever new style you want to apply to it, and then blowing the new image back up and retrieving that image. So again, like the architecture's not so important, but the intuition super important. And I don't think I want to say anything about that. The last thing we will end at is self-supervised learning. So self-supervised learning is extremely cutting edge. It is going on, it is what is going on right now. What is self-supervised learning saying? Well, what happened so far, like all that we have discussed, we had labeled samples. So I could tell you that this image is labeled horse. If I want to convert horse to zebra, this is what I want to convert it to. Yeah, I had labeled examples basically. But if I consider cases where I have massive amounts of data but no labeled examples, how do I create artificial tasks that force some sort of representation learning on these images? Well, the simple idea, oh, I thought she had an image here. Okay, now mind. The simple idea is I want to, I really saw. Yep, yeah. So this sort of idea where I want to occlude a part of the image. So if this is a dog, ignore the slide. All I'm looking at is this. Um, if I want, if I just have this image without any label, and I want to do some sort of training on this so that my classifier learns something about dogs, what I do is I train it to reconstruct the image by obscuring certain parts of the image. So I train it to make learn representations that force the representation that it learns to be closer together because they are of the same image, except with different parts obscured, if that makes sense to people. So if I have 5 images of myself, I will create rotated versions, partial versions, different color versions, different channel versions, whatever. But they're all the same image. So all of those representations should be the same. And that is how I create my loss function, where I say that the loss function depends on how far these representations for the same image are. And by doing that, I am trying to create this task, that mini task, just given some training data, just given some data, I can force my classifier to learn something meaningful. And then I can use that trained or pre-trained model for whatever other purpose I like. And so that is, if there's a question, this is where you should pause me and ask me. Okay, seeing none, I will move back to the last slide. And that is what this diagram here is trying to say. It's trying to say for the same image, if you create 2 different representations through 2 different transformations, and you pass it through this neural network that learns a hidden representation and then some ultimate representation of some output representation, then Zi and Zj, these 2 output representations of the same image X, have to be close together. That is the learning problem for self-supervised learning. And that is where I can end today's lecture and pause for questions. As a reminder, we won't have a recitation tomorrow, but we will release a sample midterm later in a couple of hours today, so that you can spend some time on it and then get back to us during the week, during office hours with your doubts. Office hours project discussions always welcome. Please ping us beforehand so we know, and we'll grade your project proposals and get back to you during the week. Okay, that's okay. Then I can stop recording.